Thank you. I am from the Diabetes Unit from the Warsaw Medical Center from Tel Aviv University, Israel. I, thanks to the organizer for letting me to present the research on the influence of the breakfast on clock gene, MPK, mRNA expression, and postprandial glycemia in healthy and type 2 diabetes. Nothing to disclose. As we know, the glucose metabolism is controlled by the circadian clock genes. The central clock is localized in the suprachiasmatic nucleus in the hypothalamus, and he is controlled by the light and dark cycle. Similar clocks are in most of the organs, in tissues, in the organisms, such as liver, gut, beta cell, muscle, and the adipose tissue. These clocks are not responsive to light. They are responsive and controlled by meal timing schedule. From the molecular point of view, the molecular machinery of the clock gene consists in clock and BMI genes that are dimerized and mediate the transcription of period and cryptocop genes. The period and cryptocop proteins resulting from this transcription dimerize and accumulate during 24 hours in the cytoplasm. Thereafter, they translocate back into the nucleus, stopping the clock. The clock BMI also mediates the transcription of other clock genes involved in the glucose metabolism like PPAR gamma, ROR alpha, reverb alpha, and together with the activity of MPK, they together regulate the circadian rhythmicity of glucose metabolism. Indeed, the clock gene in the beta cell and in the skeletal muscle, under the influence of the light and meal timing, regulate the diurnal variation of glycemic response, with higher response of the glucose after isocaloric meal in the evening in comparison to the morning. We previously have seen that meal timing influences the type 2 diabetics by showing that the overall glucose response or overall glucose excursion during the day are significantly lower during the big breakfast diet. It is consisting in big breakfast and low dinner, compared to isocaloric diet with high caloric dinner and small breakfast. More recently, we have shown the effect of skipping breakfast when we observed that the glucose response after lunch and dinner were significantly higher, and insulin and GLP-1 were significantly lower in the day without breakfast compared to the day with breakfast or yes, breakfast day. Therefore, we hypothesize that the breakfast consumption may trigger proper clock gene and MPK expression, leading to improved postprandial hyperglycemia, insulin and GLP-1 response after subsequent lunch. For this, to demonstrate this, we test 16 healthy and 16 type 2 diabetic patients, one day with breakfast and lunch, and other day without breakfast, fasting until lunch and only with lunch. And we measure in this patient the clock gene expression, MPK, glucose insulin, plasma glucose insulin, and intact GLP-1 before breakfast, before lunch, and after lunch. And we can see here both in diabetic and healthy patients, no matter what happened during the morning before lunch, we see that MPK is upregulated after lunch in the day when the breakfast was consumed, which is in green. The same happens in BMI gene that is upregulated after lunch, and P1 upregulated after lunch, and the same with ROR alpha. Similar results we see in the healthy group. When we see separately the upregulation after lunch, we observe that this upregulation is associated with significantly lower response of glucose after lunch and significantly higher response of GLP-1 and insulin after lunch. Similarly, in healthy group, the upregulation of MPK, BMR, PER1, and ROR alpha was associated with lower response of glucose and higher insulin and GLP-1 after breakfast. This was significant, although it was in less magnitude compared to type 2 diabetes. In summary, the study shows a rapid change in upregulation of clock gene and MPK expression after lunch on yes breakfast versus no breakfast day. The effect of breakfast is acute, as only one day of skipping breakfast leads to such a deleterious effect of clock gene, MPK, glucose, insulin, and GLP-1. As the same clock also influences blood pressure and atherosclerotic disease and endothelium and synthesis of aldosterone and obesity, long-term studies are warranted to determine whether the effect of meal timing on clock gene and MPK, besides of affecting glucose metabolism, also has influence on body weight, blood pressure, heart, sodium transport, PI1, and endothelial function. This is my team. Part of them is belonging to Tel Aviv University. Other from Hebrew University. Oriflow is this one who tests, who measures the clock genes with his technician. And the other part of the team is in the Weizmann Institute, and Bo Allen from Lund University in Sweden. Thank you very much.
Thank you for that presentation. Don Schwenke, via Sacramento. Would you tell us about the composition of your breakfast and your lunch? I'm interested in the macronutrients and also within the carbohydrate, simple carbohydrates, complex carbohydrate, and soluble and insoluble fiber.
As you can see here, we have all the meals was 750 50 calories. Breakfast, lunch, the same calories. And in the day without breakfast was breakfast absent, and the lunch also 750 calories. The composition was bread, white bread, granola, coffee with milk, with 1 cup of sugar. The intention was to give something not healthy. It means something that increased the glucose really to have the response, yes, better or higher or lower, or more reduced response of glucose. So it was, high glycemic index meal.
Courtney Peterson, University of Alabama, Birmingham. I have 3 short questions for you. The first one is, which tissue were you looking at these clock genes in?
Yes, I'm sorry, I realized I didn't comment this. We measured the clock gene in the white cells, and we suppose, obviously we are working with humans, it would be very nice to measure in the liver and the pancreas, but it's not possible. Nevertheless, there are several studies that have shown that what happened in the genes in the white cells is the same. It is part of the peripheral clock gene, and it is thought that they work together. It means that if you eat one day at night, another day in the morning, and you don't have a meal time schedule synchronized with the central clock, it is thought that all the genes in the liver, in the pancreas are disrupted. So we are not sure that all is true, but it is, approximation to all the peripheral clock genes.
And did you find that particular clock genes were more predictive of the acute responses you saw in glucose and insulin?
Actually, we found that because we measured 9 clock gene and also DPP4 plasma activity. Actually, I didn't mention because of the time, but the DPP4 plasma activity didn't change. With breakfast, no breakfast, there were no changes. There are other clock genes like you see CRY1, ROR alpha, reverb alpha. This clock has some changes, but not significant. But those which I mentioned, MPK, BMR, PER1, and ROR alpha, they are directly associated with the response of glucose, insulin, and GLP-1. So we think that they are more connected. We are swimming in experimental things. We still don't know what are the clock genes, what is normal, what is not normal. It is all so new, even that the change with the meal so quickly. In one morning you change the expression of the gene is something impressive that you can change so quickly. But we know this because sometimes we eat bread at night and tomorrow we have high triglycerides. So we know that the metabolism change very quickly, but it is shown in one morning. And it was shown also in animals that 2-4 hours are enough to change the clocks, the expression.
Thank you.
Thank you very much. The session has ended.